All right, so we made it through Bodhi plots. We're going to talk about filters, and then we're going to try to wrap up this module pretty quickly because I know that this has gotten to be pretty lengthy. We've gone through a lot of material, so let's cover some filters. What are filters? Let's start with that. So this here is just a block diagram I've made of what a passive filter, which is just a filter circuit that's basically made of only passive elements. Passive elements include resistors, capacitors, and inductors, right? And so obviously this isn't a circuit itself, but I just am showing that, let's imagine inside this box is a passive filter. It could look like any number of things. It could look like, might look like this, something like that. It could be an example of a low pass filter, or you see these all the times in power electronics. But just so the point here is, what is a filter? What does it even mean for something to be a filter? Basically, by definition, a filter is some kind of a circuit that favors, at the output, it favors certain frequencies over other frequencies, or it basically passes some frequencies through the filter. So some frequencies will come out untouched, and other frequencies will get attenuated. And so the question is, what does it mean for something to get attenuated? Well, let's just take a look at what it looks like. If I have an input signal, let's just say that my input signal looks like this, and I send it into some system or some circuit, and on the output, I get a signal that's much larger. This system amplified the input, right? It amplified it. That's the definition of amplification. When the output is larger than the input, I have amplified. However, if I have the same system, or sorry, not the same system, but a different system, just put it down here, and instead of getting a larger output, I get a smaller output. So something that looks like that. That is called attenuating. Okay? So to attenuate. In this case, out is less than in terms of the amplitude. In this case, out was larger than in, right? I guess that's pretty clear. And so what a filter does is, in particular this figure, I'm showing that this signal at a frequency F1, let's just call it F1, this signal was able to pass through the filter untouched, right? Has the same amplitude and the same phase as it did when it went into the filter. The signal is exactly the same. However, this other signal that's at a different frequency, F2, I have the same signal in the background here, kind of opaque, so you can't really see it, but it's there so that you can reference it. I'm showing that this new signal, the output right here, has been attenuated, right? It's at a much lower amplitude than the signal was at the input. And so that's an example of what a filter does. It will allow, this same circuit would allow this signal to pass through untouched and come out the other side, be at our output. And this signal, which is the same amplitude, right, but it has a higher frequency, that signal gets attenuated. Okay, so that is basically the definition of a filter. And it could go the other way. It could be the case that the higher frequency signal was able to pass through and the lower frequency signal was not able to pass through. Or signals at frequencies below and above a particular range of frequencies were allowed to pass through, but then this middle range was not allowed to pass through, okay? And we're going to look at those types. Those are basically the four main types of filters. I'm going to talk about them right here. So let's just sketch this. Let's say that this is the ratio of my output to my input. Let's just do voltage for now because it just makes more sense. And let's say that it's 1 here and 0 here. I'm looking at a range of frequencies. F, for a low-pass filter, an ideal low-pass filter, it would pass all frequencies. So V out would be equal to V in up to a certain point. And then right at my cutoff, FC, that's where the filter would cut all the frequencies above that value. And that is why it's called a low pass filter, because it would pass all the low frequencies compared to my cutoff frequency. And then all the higher frequencies would get sent to zero. This is what an ideal low pass filter frequency response looks like. This is not something that we can realize in real life. This is ideal. Ideally, this is the cutoff that we would want. We cannot, this is not practical, okay? We can get close. We can try our best to create something practically that will behave like this, but we're never going to get something that can have such a steep drop off, okay? So we're going to get to that point. I have a slide that compares ideal filters to practical filters, and we're going to talk about that when we get there. But let me come here too and just show you what a high pass filter looks like. I'm sure you may have already figured out what it's going to look like. Here's my cutoff frequency, V out over V in. We'll put my 1 here and my 0 here. And a high pass filter will not pass the low frequencies. And then right at the cutoff frequency, it will pass all the frequencies above FC, okay? So that is an ideal high pass filter, ideal frequency response for the magnitude. Okay, I've got 2 more types of filters on the next slide that are pretty self-explanatory. I think let's go with, let's do this real quick so that we don't run out of time, or so that I don't make this video too long. I think that you could probably guess what these look like, but nonetheless, I'm going to draw them and explain them anyways real quick. So the ideal band pass filter has a FC low and an FC high, basically cutoff, a high frequency cutoff and a low frequency cutoff. And this filter will cut all these low frequencies out. It will pass this particular band of frequencies that I specify between the high and the low cutoff, and then it will cut all these low frequencies out or these high frequencies out as well. So it's called a band pass filter because it passes a particular band of frequencies, and that band, the difference between the high and the low, is called the bandwidth, which makes sense. It's literally the width of the frequency band that it passes. Okay? And so what about a band reject? I'm sure that if you're with me at this point, you could probably guess what a band reject filter would look like. But it's basically going to allow all the frequencies to pass except for this band, which again, that band would be characterized by the bandwidth. FC high minus FC low would be equal to the bandwidth of this band reject filter. Okay, so those are the 4 types of filters that we're going to be looking at. We might look at other types of filters, but by definition, anything that doesn't have a uniform frequency response, so basically anything that doesn't have a flat response, is a filter. It has a filter basically is just saying that it responds differently to different frequencies, okay? But these are the types of intentionally designed filters that you will see the most commonly. Low pass filters, high pass filters, band pass, and band reject. And these, again, are ideal frequency responses that I've shown here, right? These are not practical. To design these circuits practically, we're going to talk about that as we move forward, and I'm going to show what practical responses of these circuits would actually look like. But the goal is for a low pass filter to pass low frequencies, high pass filter to pass high frequencies, and so on. Okay, so I'm going to end this video right here, and in the next video, what am I talking about? Oh, I'm talking about ideal versus practical filters. Awesome. All right, so I'm going to end it right here.